Sure, sure. I think that should be okay.
Okay.
Yeah. Okay. Um, okay. Does everyone see my screen? You should see a piece of paper here. Yes.
Yes.
Okay. And hopefully it's not mirrored because well, I see it mirrored, but I think it should be correct for you. Okay. Good. So we were discussing dynamic programming, and so maybe I'll just go over what we did in dynamic programming. So the first thing we did was we taught, or rather I taught this algorithm for the 0 and knapsack problem. And towards the end, we were discussing this problem of longest common subsequence, which is a very classic dynamic programming problem. So I'd like to go over a solution of this in reasonable detail, show you the table, how everything, the recurrence, the table, and the ordering to fill things up. And that should, hang on, let me maybe, I hope my screen is clear. Yeah, everything looks good. Okay. So in the problem of longest common subsequence, so first, that we discussed what is a subsequence. So a subsequence of a string is formed by taking a subset of the characters in the same order. So for example, if you take the word string, you can take any subset of the characters in that order. Okay, so you could take sing, for example. You can take sin, you can take ring, you can take tin, you can take t, n, g, any combination. And as we discussed, there are 2 to the n, many subsequences. Remember, the difference between a substring and a subsequence, in a substring, they have to be contiguous. So for example, ring is a substring and is also a subsequence. Okay, so a substring is a subsequence, but a subsequence might not be a substring. Okay, and so the problem is, given 2 strings, find the length of the longest common subsequence, also find the longest common subsequence. And this is a very important problem. If any of you have used the diff utility in Linux, it's basically doing some version of longest common subsequence. And longest common subsequence, also known as the LCS problem, is used in genome sequencing. So it's a very important problem that is studied. And so the LCS problem is given 2 strings, find the length of the longest common subsequence, as we just said. And usually the way that this problem is set up is that there are 2 strings, one of length m, one of length n, and we'd like to get an algorithm whose running time is polynomial in m and n. And so the way that we approach any dynamic programming problem is to first design a recursive algorithm. Once we have a recursive algorithm, we can set up a recurrence. And once we have the recurrence, we can design the dynamic programming table. We look for overlapping subproblems, look at the table, so on and so forth. And so I'm actually just going to rewrite what I've drawn over here so that we can go over it more slowly. Okay, so let's begin by, so as we discussed towards the end of last lecture, I'll do this again, is we have these 2 strings. I call them A and B. And so let's look at the last character. And remember, the length of this is n, the length of B is n, and we're looking at just the last character of these 2 strings. So if these last characters are identical, Right? I'm just thinking of these as lists and I'm indexing. So m minus 1 corresponds to the last index. So if these two are the same, then what I can do is in the LCS, I can just match these to each other. Right? And so in this case, the LCS is the LCS of A going up to m minus 1. So I just look at what remains, find the LCS in these two, and I add 1. Okay, I want to be a little careful here. So why do I have to match the last two characters to each other? Maybe in the LCS I want to actually match it differently. Does anyone have the answer? Why should I be matching these last characters to each other? Any guesses? Someone said can't double count on recurse. Not sure what you mean. I'm just saying that why is it the case that I should do a recursive call for LCS m minus, I should say m minus 2, I'm sorry. Right? I'm reducing the index by 1. I'm reducing the index by 1. So maybe it's worth explaining this. So here's what I'm saying. So suppose you take A and B, and you consider the LCS. Now, what I'm going to say is either, so I'm looking at this situation where the last characters are actually the same. Last characters are the same. Yeah, by the way, LCS is longest common subsequence, not substring, longest common subsequence. So either am minus 1, which is this last character, is matched or not. So what do I mean by matched? I mean is part of the LCS. Okay? So either this is matched or not. Now I'm going to show you, I'm going to prove that there exists an LCS. So I say and because there could be multiple longest common subsequences. I'm going to say I'm going to show that there exists an LCS where am minus 1 is matched. Okay. Any questions about did you understand why I'm trying to do this? I'm trying to argue this to show that if the last two characters are the same, then we can just match those characters to each other and just recur on the left, recur on the remaining part. And that is this first case of this recursive algorithm. Okay. Questions? I'll just take a short pause. Okay. Okay. So I'm going to prove that there exists an LCS where am minus 1 is matched. Okay. Now suppose not. Further, suppose B n minus 1 is also not matched. Okay, now my question is, can this happen? And I can do zoom polls here. I still keep the same options. Red is yes, B is no, and this is maybe. Okay, and I'm just going to launch my poll. I'll give you maybe a couple of minutes to think about what the answer is. Can this happen? Okay, you can see what the results look like. Actually, most of you got this wrong. The answer is no. This cannot happen. Does anyone who showed why it cannot happen want to say why this cannot happen? Or does anyone want a reason why is it that this cannot happen? Why is it that if a and minus 1 is not matched and b and minus 1 is not matched, this situation cannot happen? Remember, it's an LCS. It's a longest common subsequence. Yes, any guesses?
I maybe have a clarifying question about what the thing is asking for.
Sure.
So you're asking if there is a case where neither a minus m or a of m minus 1 and nor b of m n minus 1 don't get matched. Like both
Correct.
of them aren't matched.
In a longest common subsequence.
Okay.
Does that clarify your question?
Yeah.
Okay, good.
To answer your question, I
Yes.
think maybe it cannot happen because most simply because they're not common. It doesn't satisfy the requirement of the problem.
Hang on. In this case where I'm assuming the last two characters are the same. Does that make sense? So I'm looking at this situation. Assume that the last two characters are the same. And if the last two characters are the same, I'm claiming that in an LCS, you cannot have a situation where both of these are not matched.
I have a clarifying question.
Yep.
Could you define matched?
Matched. Okay, so good. Maybe this is let me just do a different picture here. So I think this will help explain. So how does it? So let's just take this example that I had of string and spin. And we argued that an LCS is sin. So how does it work? You say, I match this S to this S, then I match the I to the I, and the N to the N. So in general, the way the picture looks is if I have these two strings, and I want a common subsequence, I'm going to take some characters from here, right? And I'm going to find the corresponding characters in here. And so what I do is I have to sort of pair them up. And this is what I call, I'm matching them. This is like the pairing up or the matching. So this is what I call a match. So these characters, which I've shaded, the shaded characters are matched. And what this means is they're part of the LCS. And the unshaded are not matched, which means they're not part of the LCS. Does that explain what this means?
Yes. Yeah. Thank you.
Okay, so now if you go back to this question, does everyone see what's going on here?
Yeah, I think it's basically imagine we had a longest substring for the n-2 characters, right?
Right.
We could always, if the last two are equal for both strings, we could always extend it by one, match the last two, and we'd get a longer substring. So
Subsequence.
Subsequence. Subsequence.
Yes,
Mhm.
exactly. You're absolutely right. So the idea is, suppose the longest common subsequence did not use these. So look at the longest common subsequence of what's left and just match these or pair these up together, and you'll only make it longer. So just to go back to an example here, suppose if I took string and I took sing, so these two are the same. And if I didn't use both of them, then I could find the longest common subsequence on what's left and then add these together. So that means that one of these, well, actually in this case, both of these have to be used. So if both of these are not used, that's a contradiction to being a longest common subsequence. Okay? So this cannot happen because if both am-1 and bn-1 were not part of an LCS, we could add this. So we could add this character because we know it's the same character, which means, or we could match am-1 and bn-1 and extend the longest common subsequence. But that's a contradiction because you cannot extend a longest common subsequence. You cannot make it any longer. So is this clear? It's a bit hard for me to tell over Zoom whether people are following or not. So either, I get something in the chat or, okay. So that's why what I'm saying is this cannot happen. Okay, now I'm going to ask you another question. So we know that, remember, we started off supposing that am-1 is not matched. Now we said, suppose bn-1 is also not matched, that cannot happen. Therefore, bn-1 is matched. So what this means is the picture looks like this. This is A, this is B. Yeah, someone had a question? Okay. So we know that this is matched. So we said this am-1 is not matched. But bn-1 is matched. But it's probably matched to something over here. Okay? Okay, now here is another question, so I'm going to maybe I'll keep this out of the way and go back to it for drawing examples. And here is my question. Remember, this is what's happening in the LCS. Can I change the LCS to make Bn minus 1 match with Am minus 1? Yes? No? Third question is, I don't understand the question, because I want to make sure that you follow. Okay.
And maybe a clarifying question.
Yeah.
This is asking considering all three of those characters are the same.
Exactly, right? So yes, we're assuming that all these three characters are the same. Because we're in this case where Am minus 1 is equal to Bn minus 1. Yes. All right, there's a fair number of people who say that they don't understand the question. So maybe, I'm going to restate what I'm asking, and then, but this is a good place to interrupt me and clarify. So what I'm saying is, okay, so let's kind of maybe step back a bit, and I'll keep the poll open, and people can continue to answer. We're in the situation where the last two characters are the same. I'm just trying to understand what happens in this situation. Now, I wrote something here, but I'm trying to justify why this is the case. Okay, so let's keep that aside. So what am I saying? I'm saying consider the longest common subsequence. Either Am minus 1 is matched, which means it's paired up with someone, or it's not. I'm going to prove to you that there always exists an LCS where Am minus 1 is matched. Okay. Suppose not. And suppose Bn minus 1 is also not matched. We argued this cannot happen because you can always extend the LCS by matching Am minus 1 and Bn minus 1. So we're in a situation where Bn minus 1 is definitely matched. I am asking, could you somehow change this, get a new LCS where Bn minus 1 is matched to Am minus 1? Okay, so to draw an example, well, actually, let me ask the question and then I'll show you the example. Okay? Does the question make more sense now? Hopefully, there's still confusion here. So, someone said it makes less sense now. That would be a good time to ask me a question as to why it's making less sense. Okay, so maybe an example is what you all need. Okay. So here's an example. So let me now give you a different one. I'm saying I'm going to construct a new string, str, and maybe there's. So think of this as some long string. It's got a bunch of things here. And let's just say we're just trying to find sing, right? And this is something longer, just to keep it simple. So I'm saying, suppose I told you, so we know that in the LCS, the G's have to be matched to each other. Or, no, sorry. What we know is that both these G's cannot be unmatched. We're assuming the last G over here is unmatched. Now I know that this G over here has to be matched, and I'm matching it to that. My question is, could you change things so that this G over here is actually matched to the last G over here? That's my question.
Sorry, but what I don't get is we already stated that they match, that they are equal. So why are they not going to be equal now?
Because you don't know
We
what
already
the
stated.
longest common subsequence is doing. When there are two choices, you don't know which one it's going to, pair up with.
If you added another G to sing, it would match the last
Correct,
one,
but-
right?
Yes, but I'm just having one G over here.
I thought the question was if you could add another character to the...
No. The question says, can I change the LCS to make Bn-1 match with An-1? Can
Change
I modify
means
things?
reduce it, or...
No, modify. Find another. So the longest common subsequence is not unique.
Okay.
Maybe that's the thing that's throwing many of you off. The longest common subsequence is not unique. I'll give you an example. I'll give you a very simple example. Suppose I take the strings xxy, I take xy. Is the longest common subsequence unique over here? No, right? Because I could basically, this y has to match with this y over here. But the x basically has two options, and it could match with either of them. So the longest common subsequence is not unique, and that's why I'm asking, could there be a different longest common subsequence which matches the last two characters with each other? Does the question make more sense now? Maybe I'm just going to relaunch the poll now and allow you to answer again. Okay, so I think now most of you are seeing what the answer is. I'm just going to end the poll. This is now it makes sense. So you see that you can always switch it to match with the last one, because that's not going to create any problems. So maybe this is also worth drawing out over here, that when you have this sort of matching, like I'm matching characters to each other, right? I'm just going to draw the things. Can I do this? Can I match it this way? Can this give an LCS? Just to check your understanding. relaunch the poll. Can this happen? That's right. I guess someone did give a spoiler. No, it cannot happen because it breaks the order, which is absolutely correctly written. So this cannot give an LCS. No, because it breaks the order. So you have to, because that wouldn't. So for example, if you had SING here and SING here, or sorry, SIGN, that gives sine versus sing. Right? So you can't match sine to sing because you cannot change the order. Okay? Okay, so good. Okay, so now I feel we're all getting on the same page now. I should have maybe given these examples earlier. So what is the punchline of all of this? The punchline is if am minus 1 is the same as bn minus 1, there exists an LCS that matches these characters to each other. Okay? And this now goes back to our original picture that if the last two characters are the same, I can always match them to each other, reduce the lengths by 1, and make a recursive call. Any questions at this point?
Maybe
Yes.
a stupid question. Does it actually matter which character matches to which as long as you have the same character?
Same length, you mean?
Or as long as both of the characters are the same, does it matter if A matches it or B matches it?
Well, it's not A matching or B. It's A is matching to B. So think of it, you're basically pairing these up to each other. So maybe the example is to, again, go back to this. It's like you're pairing up something from A to something from B. Now the question that is, which things need to be matched to each other? So again, just to maybe build on this example over here, suppose I took string here. Okay? And then I took SINTG, okay, as my others. So I could decide to match this T to this T. But is that a good choice?
No, not really.
No, why not?
Because you can get a longer.
Exactly, right? So that was a bad choice to do. So the right thing to do is to get sing. But now suppose, so I know that this S has to be matched, and let's say there's an S at the end. This is also a bad choice. Because this S has two options, and it should actually match to the first option. So figuring out which is the right option is basically the heart of this problem. Does that answer your question?
Yeah, kind of. I guess my hang-up was the matching part seemed directional, like A matches to B or B matches to A, but it seems like it doesn't really matter.
It doesn't matter. Yeah, you're right.
Yeah.
Okay, good point. So it doesn't matter whether you're matching a character from here to here or here to here, because they're really the same thing, right? You're pairing things up, right? You're pairing up characters, and in the pair, it doesn't really matter whether you pair up from the first to the second or the second to the first. Does that clarify?
Yeah, that sounds good. Thanks.
Okay, good. Okay, good. So our main punchline is that if AM minus 1, the last characters are the same, there exists an LCS that matches these characters to each other. And so now we need to understand what happens if not. So suppose am minus 1 is not equal to bn minus 1. So just, maybe this character is a G and this is a T. So rather curiously, I'm ending up with DNA sequences as well with T and G. So that was not my intention. But anyway, okay. So now let me ask you another question. In the situation, yeah, someone raised their hand.
Yeah, sorry. Okay, so just like looking at the punchline, like we're saying, like if am minus 1 is equivalent to bn minus 1, there exists a longest common substring that matches these characters to each other. And we're saying subsequence, sorry, longest common subsequence. And basically, like, is the argument that like the longest common subsequence could just be those two characters at the end of the day? Like, therefore, like it has to exist?
We're not saying that. No.
Oh, okay.
What we're saying is that if you have any longest common subsequence, you can start with it and kind of change it so that these two match with each other.
Okay.
So it's like saying that if I have any two strings where the last characters are the same, then there exists a longest common subsequence where those last two characters are matched to each other.
But that doesn't happen.
Yeah.
Wait, sorry, what was that?
No, sorry, I was going to say that it doesn't need to be like that. Like there can be another longest common subsequence that does not meet that property, right?
Exactly. So I did not say that all longest common subsequences have that property. I said there exists one that has this property. There exists. So maybe the important thing is that.
Okay, thank you so much.
Does that clarify? Okay,
yes.
Good. Yes. That's right. So as someone put in the chat, it just means that this is an available option. Now the next comment says, it is always part of a valid LCS. So this is where it gets a little complicated. So just to give you this example here, there do exist LCSs. That is, there do exist long and common subsequences where those two are not matched to each other. But what it's saying is it's always safe to do that because there will be a longest common, an LCS that does match it. Okay? So that's why, now this is really important because that's why you can actually apply this recurrence. That's why you can apply this recurrence. Because what you're saying is, look, if these two things are the same, there always exists a solution where these two are paired up. So let me go ahead and pair them up and then apply recursion. It is not saying that all solutions must have that property. And indeed, like the question of finding all solutions is much more complicated. Okay? Okay. Good. So let's proceed. So now we're looking at the other case, which is suppose that these two last characters are not the same. Now here's my question. And it's worded carefully, so please read it carefully. Let me try to write this carefully because there's lots of double negatives and ands and ors and everything, and I don't want to confuse everyone. So here's my question. What do I want to say? I want to say that okay, so I'll write this in the simplest way and then I'll clarify. Neither am minus 1 nor bn minus 1 participate in an LCS. Is this true? Is it false? Or is the question not clear? Okay, so thankfully, from most people seem to be getting towards the right answer. The funny thing, and this is my mistake, is that when I teach this, I've just stopped giving any examples because I'm so used to thinking about this problem abstractly that it's good that you're forcing me to come up with actual examples of strings to put in. For me, it's all just indices. It's just indices and like these vague pictures. But I think putting actual strings there is helpful. Okay, I think most of you have given the right answer. And that is good. So you see that this is false. Maybe one of them does participate. Maybe one of them does participate. And just to give some sort of example over here, here's a good example. So again, we know that sing is the longest common subsequence. And so this last character is participating, but it's actually matching with this one over here. So if the last two characters are not the same, it is not guaranteed that you can just remove those last characters. So that's why in this situation, what this means is we cannot just call LCS of A going to m minus 2 and B going to n minus 2, right? This would not work because we're dropping that last character and we might lose. So neither an minus 1 nor bn minus 1 participate in LCS. And this is maybe a very simple question, but never wrong to ask something that is easy. Can both am minus 1 and bn minus 1 be in an LCS? Yes, no, maybe, but maybe not. Can both of these be present? Okay, so this is actually a good time for me to pause. So I'm going to let this poll running. I'm going to pause for a bit, and I'll take any questions on the chat. I'm just going to step out for just a minute, so you can put your questions in chat. I'm going to step out for a minute. I'll come back and then answer all these questions. Okay, I'm back. Okay, someone asked, this is assuming am minus 1 and bn minus 1 don't match with each other. It's assuming they're not the same character. That's like the right way of phrasing this. Okay, I'll just, maybe pause for another minute or so that you can stretch your legs, step out, get a snack, or do whatever. All right, let's get back. Okay, so while clearly the most popular answer is the correct answer, it's not an overwhelming majority. So I think that this is something that is worth clarifying. So the answer is no. They both cannot be in an LCS. But does someone want to say why that is the case? Yeah, why is it that both of them cannot be in an LCS? So here's an example, right? So the last two characters are not the same. Why can't both participate in the longest common subsequence?
Isn't it like, oh, you
go
go.
on.
Maybe for that to be possible, it would have to be out of order.
It would have to be out of order, exactly, right? So either that means the G would have to go to something before, and the T would have to go there because they can't match with each other, and then you would break the ordering. Exactly. Someone else had something to say?
Yeah, I was going to say the exact same thing.
Okay, good. So, because if you did that, you would break the ordering, right? So they both cannot be in an LCS. And just to write out this answer, otherwise the ordering gets broken. Otherwise, the ordering gets broken. Okay, so they both cannot be in an LCS. So what you have is a situation where, again, am minus 1 is not equal to bn minus 1. So just to put an example, that's G, and that's a T. So we know that it could be the case, so both of them cannot participate, but one of them might participate. One of them might participate, right? So both don't participate. Both cannot be in an LCS, but one of them could be. And so the question is, what recursive calls should we make now, since we know the fact that both of them cannot be part of the LCS? So again, we don't know.
we could take the minimum of the LCS of A or all of A and then B just until Bn minus 2, and then all of B and A until n minus 2.
Right, and yes, not the minimum, but the maximum. Right? You want to take the best one. Right? So you take the maximum of A, maximum of the LCS of A m minus 1, which is everything, and B going to n minus 2, and the LCS of A going to m minus 2, B going to n minus 1. So you can either drop this character or you can drop this character. And by that, you're getting a smaller recursive call in both cases. Right? And that's the argument. Okay, is that clear? Questions? So that, when we put it all together, will give us our final dynamic, will give us our recurrence. So actually, let me number the pages, 35, 36, 37, okay. So, and just to sort of, to simplify the notation, I am going to, let's see what, one second, I'm just going to rewrite as follows. So I'm going to use LCS ij to denote the LCS value of A going up to index I and B going up to index j, right? So this is saying that look at the prefix of the I and prefix of the j. And so here is my recurrence. Here's my recurrence. I'll say LCS ij is equal to the following. So I'll say this is just the LCS of I minus 1, j minus 1, plus 1 if AI is the jth character of B. And otherwise, it's the max of LCS ij minus 1 or I minus 1 j. Okay? Is this clear? Any questions? Okay, good. So this gives me my recurrence. If I were to run this just as a recursive algorithm, how long will it take? Like, will it take polynomial? Will it take exponential? What's going to happen? Okay. Why exponential? You're right that the answer is exponential, but why? Because every call makes 2 recursive calls, at least. It actually makes 3 recursive calls, right? And it's just going to, because there are 3 recursive calls that all make 3 recursive calls, so on and so forth. The recursive calls, yeah, it's even worse than doubling. It's actually tripling because there are 3 different, well, you're right. It's doubling, I'm sorry. Because depending on the case, you could be doubling your recursive calls. You're right, doubling. Okay? So this is where, but we start with the recurrence. Now we're going to see the overlapping subproblems. how many different arguments are there? Where by different arguments, I'm looking at the entire, like the whole tuple as an argument. So think of this as looking at the tuple of the argument, like all the arguments. How many different possibilities are there for the arguments? Okay, so maybe I'll ask this as a question. Okay, is it m plus n? Is it m times n? Or is it 2 to the n times 2 to the n? Okay, so let me relaunch my poll. How many different arguments are there? Like if you think of the entire tuple of arguments. You know, it's amazing. Multiple choice questions are really amazing because they make it so clear how many people understand. Whereas if you give prose type answers, then people will say all kinds of things. With a multiple choice question, you have to commit, right? It's like you have to make a choice and you have to call it. So they're great. And I think they really help clarify. Okay. Okay, again, I'm not, I think, again, a majority, or rather the most popular answer is correct. But it's not an overwhelming enough of a majority that I'm confident of continuing. So let's get this clarified. You're right, the answer is m times n. Why is it m times n?
Because for every m, like for every character or character in m, it has to go through all of the characters in n essentially to find, or I don't know, maybe I got the right answer for the wrong reason. Sorry.
Yeah, but I think there's an even more direct answer. Yes, someone says Cartesian product, which is absolutely right. It's fairly direct, right? Like there are two arguments here. How many choices for this argument? M choices. How many choices for this argument? N choices. Right? Because this goes from 0 to m minus 1 and this goes from 0 to n minus 1. So there's only m times n choices. So even if you run this exponentially, there are only m times n choices, and that's the overlapping subproblems. So I really wanted to put this, side by side together, which is this is how you approach a dynamic programming problem. You come up with a recurrence, you show the overlapping subproblems, and now finally we're going to build the table. Okay, so is this clear? It's m times n. There are only n times n possible problems one can come up with. And so this is now suitable for dynamic programming. And so now we're going to set up so we'll set up the dynamic programming table. Okay, so now my question is, what is the dimension of this table? It's going to be 1, it's going to be 2, it's going to be more. So remember, we have a dynamic programming table. Given you have this recurrence. What is the dimension of this table? What is the dimension? Okay, I think I'm getting a pretty good vibe from the answers I'm seeing so far. Okay, and most of you are absolutely right. The answer is 2. There are 2 dimensions. And why are there 2 dimensions? Because there are 2 arguments here for m and n. And so here is how the dynamic programming table looks like. So I'll say this is the index of A, and the other side is the index of B. And just for convenience, I'm going to sort these in decreasing order. So I'm going to start with the index going from n minus 1 to 0 and n minus 1 to 0. Okay, and this is just so that the top left square is the answer that I'm looking for. And so what is the base case? These over here form the base case. And so what is the base case here? The base case for the recursion would be the LCS of 0 with some I, or, I'm sorry, I should probably put J here, and I with 0. Okay, so I'm just looking at this question in the chat. As an aside, if the number of arguments to the recursive function, typically, if the number of arguments gives you the dimension of the table. Yeah. Okay, so how do you solve LCS of 0j? How do you solve this base case?
Doesn't that just mean there's no common characters?
So give me an algorithm that solves this case. Yeah, you're almost there. So what does LCS of 0 and j mean? It means one of the strings is just a single character, and the other one is something longer. How do I solve LCS over here?
You loop through the string and see if it matches the single character.
Exactly. Just look up this character, right? All you do is look for the character in here. So you just look whether this character is present anywhere. And if it's present anywhere, the LCS is 1, otherwise it's 0. Right? The LCS in these things is going to be 0 or 1. And if you think about it a little carefully, in linear time, which is a single for loop, one can compute LCS 0j for all j. So I'm saying it's even better. All you just do is, if you just do one loop, you can get all these. And so this will basically take time O of m. So overall in time O of m plus 1, we can compute all base case values. Okay? And so now we just need to do how to fill up the table. Like, what is the order? Right? So if you have some ijth entry here, if you have some ijth entry here, how are you going to find out how to fill this up given this recurrence? Pretty much showing you what the recurrence is. And so what is the order in which you should do it?
I was gonna say you should start like it would make sense to start at the end of the longer string, but it also doesn't really matter.
It doesn't matter. Exactly.
Yeah.
Yeah. So what should you do? How do you fill it?
You look at the cell on the right and the cell below and take the max of it.
Exactly. So you have two situations. So either you need to look at this cell, right? That could happen in this case. Or you have to look at this cell and this cell. So as long as you filled up the values in these three cells, you can fill up the table. Right? And so what is the order in which you do it? You could go row by row or column by column. Let's just say we go row by row. So you fill up a row, and in each row you go in reverse order, right? So you fill up this row, then you fill up this row, then you fill up this row, and in this row you fill up in this order. You keep going this way. And if you fill this up, then you'll fill up the entire table. Let me just write down the pseudocode for that clearly so that everything is precise and stated. And then I do want to call out a few things on how to write solutions for dynamic programs. Okay, so what we'll do is we'll just say for I going from n minus 1, I'm sorry, the other way around. I should say from, I'll say 1 to n minus 1. For j going from 1 to m minus 1, we can just say that LCS of ij is equal to, so we can just put down this recurrence here. Okay, so maybe I'll just state this even more carefully. I'll say if AI is the same thing as BJ, then the LCS of IJ is equal to the LCS of I minus 1, J minus 1 plus 1, and else the LCS of IJ is the max of the LCS of I minus 1J and I J minus 1. Okay, so this gives the entire algorithm, and what this tells you, these loops tell you, is the order to fill up the table. So what I've written here is pretty much the entire code. Are there any questions about this?
Yeah, like I feel like we ended up with the same solution
Same solution as
the previous one that we stated that was in polynomial time, in exponential time.
no, this runs in polynomial time. What is the running time of this algorithm?
But if you look at the other one, it's just
Sure.
the same.
This one, you mean?
Yes.
Yes.
Well, it feels to me that it's the same. So
the thing is, the dynamic programming algorithm is very similar to the recursive one, but you build it in a table rather than doing recursion.
yeah, but where are we using well, for my understanding, what we need to do in the final algorithm, the dynamic programming one, is to look at the table if we haven't seen them.
Exactly. You can also do it recursively and memorize solutions and store solutions. Remember, this is there's a comment made. This is not a function call. It's a table lookup.
Oh, okay, that was what I was
Okay,
missing.
so maybe, sorry,
Yeah.
I should do this. I should put, yeah, this is my fault. I should make these as square braces, right? So this is a table, not a recursive call.
And like in a real algorithm, it would be like if it's not in the table, go and look for it. Like do
Yeah,
the call.
but we have set this up in such a way that the table is always filled up because we're filling it up in the right order.
Okay.
Does that make sense?
Yes.
So someone said a lazy function evaluation with caching could avoid this table mess. I actually don't think the table is messy. It's actually quite simple. It's just a two-dimensional array. I mean, if anything, I would argue that your lazy function evaluation could, if you don't do it carefully, it's much easier to debug this code than to debug that code if you make errors.
Just for like a wrap up. First, we fill the table. If there's no value in the table, we fill that, like as we said, and then we look through the table. That would be it.
You don't even, you're basically, to fill up an entry in the table, there are just these entries you need to look up, which you've already filled up because you're going in order. Does that make sense?
Yes. Yeah, ready.
Yeah, okay. Any questions? So I just want to sort of reiterate a particular point here, which is that for giving a dynamic programming solution, so you have to, like when you're doing this in the homework, this is the way you should state it. So you give the recurrence, and then you explain why recurrence is correct. Then you explain overlapping subproblems, which is just what you do is you bound the number of possible arguments. Then what you do is you give the recurrence, you give the overlapping subproblems, you describe the dynamic programming table, and give the order to fill it up in. Finally, you do a space complexity and time complexity. So space complexity is the table size, and the time complexity is the time to fill up the table. And so in this case, both the space, which is the same thing as the time, is O of m times n. Okay, is this clear? So I want this structure for any solution to a dynamic programming problem. A recurrence, overlapping subproblems, describe the table, and then give the space and time complexity. Okay, any questions about this? Any doubts? So someone asked, do we do bottom up with a table as opposed to caching with recursion just to avoid the recursion overhead? So, well, okay, so in implementations, yes, although in some cases maybe you want to do it, but I think from a conceptual perspective, understanding the table is very helpful because really that is the heart of dynamic programming. Usually you kind of think of it in terms of a table and then you kind of go from there. What would be a scenario where the table dimensions are more than 2? There exist dynamic programming problems. Let me see if I have any examples. I think the ones that I am teaching are not necessarily higher dimensional, but I will see if I can come up with any examples. Usually, any situation where you actually, no. When we talk about topologic, when we talk about finding longest paths in DAGs, we'll see other kinds of tables pop up. Okay. I hope this is clear. This part over here, and this is important for homework 3 and 4. So homework 3 is about coding a dynamic programming, and homework 4 there are more algorithmic assignments. How can I show the correctness of the... Okay, so the correctness, technically, it's the correctness of the recurrence which is important. And this is what we did, right? We went through the explanation of why the recurrence is correct. In your case, I'm not going to ask you to think about it, to write a full formal proof, but I do want you to write the recurrence and give an explanation. Once you write the recurrence and you give the overlapping subproblems, the proof is fairly straightforward in the order that you fill it up in. The ordering gives it to you. And as someone said, I agree that it is easier to think top-down, but usually when you do the implementations, bottom-up is usually how you do the implementation. And you see that it's usually more efficient to do it bottom-up. And so it is this, and the reason why I do not necessarily give the caching view is that because I feel that I want you to get that bottom-up perspective. Should we give a formal proof for the recurrence? I mean, you should give some argument as to why it's correct. But, again, I don't want your proofs to run in like long-winded, too many pages. Like, just give usually in these situations, if you write down the recurrence, you can give a small argument as to why it is correct. Okay. So I guess my question is, do you want to see more examples of dynamic programming? And I'll just relaunch the poll, and I'll just say that red is yes and blue is no. Do you want to see more examples of dynamic programming?